All right. Welcome. We're going to do some limiting reagents here. Welcome back to chemistry. We're going to add it full swing. This is some pretty tough stuff. We're actually only going to go through 3 example problems today, but it is going to take a little bit of time. Before we get on to that, let's take a little step back. Are we a pro at mole to mole conversions? Are we? Cool. Then we're ready to roll. Are we also a pro or really comfortable with, at least for mass to mass stoichiometry problems? Grams to grams. If we are, cool. If not, take this as a red flag. You might have to really take your time with these notes or backpedal a little bit, look at some old stuff, and then come here. But in any case, when we've looked at chemical reactions, we've kind of assumed that we've had a perfect recipe of all the stuff we need. But that's rarely ever going to be the case. And I like to use the example of a bicycle factory. Let's say if I had a theoretical bicycle factory and it had 1,000,000 tires, but I only had 3 bicycle frames. How many bikes could I theoretically make? Well, 3 bikes. Even though I have 1,000,000 tires, I only have 3 bike frames, so I'm going to run out of something, or I'm going to have a limiting reactant or a limiting reagent in my chemical reaction. Something is going to get used up all the way first. And here's how we do it. There's kind of 2 ways. You can have, let's say, for this first method here, let's say we have A plus B gives us some product we'll call AB. So just some generic reaction. You can, for this first one, to figure out which one's going to be limiting, you can convert grams of A into grams of B. So that mass-to-mass calculation, and then compare the 2. We're going to do a couple examples there in a second. And the other way to do this is to take something. So if I had A and B, we could convert both of these into our product. Now, there is going to be time and place of which one's going to be better. So, for example, method 1's going to be really good if you're only looking for what is the limiting reactant. What is preventing us from doing this? But if we're looking for how much you would make, method 2 is going to be actually better. Because theoretically, if I, back to my bicycle tire example, if I had 1,000,000 bicycle tires and only 3 bicycle frames, we could make 3 bikes. That's all we can make. And sometimes it's more helpful to convert into that. So, with that being said, let's look at an example using kind of just this first question right here. We have 12 grams of hydrogen peroxide are used up to produce oxygen and hydrogen gas. How many grams of each gas is produced? Well, first off, we got to write our chemical reaction. Let's try that out. So we're going to have H2O2, that's hydrogen peroxide. I wouldn't expect you to memorize that. That's just, anyways. Produces hydrogen gas and oxygen gas. Now, some students are going to look, I see the problem. This is super smooth. There's going to be 6 grams of one, 6 grams of other, because we just took hydrogen peroxide and split it in half, right? No, you can't kind of make those assumptions because hydrogen and oxygen are not the same mass. If I were to look at those bicycle example again, if we were to split a bicycle up into tires and bicycle frame, even though the frame is one piece, it's actually heavier than the tires. So we can't assume it's an equal split of mass. You can't do that. Instead, we can convert into grams. So we should be kind of pros at this point, so I'm going to kind of zoom just a little bit. If I start off with 12 grams of hydrogen peroxide, and then we go into grams of hydrogen, let's just do it out. So equation's already balanced anyways. Okay. We have grams of hydrogen. Grams of hydrogen is going to go down here, hydrogen peroxide. And we're going to go to moles of hydrogen peroxide, H2O2. We can convert moles of H2O2 to moles H2. And then we convert moles of H2 2 grams of H2. Okay. Looking at our numbers, where we get them from, the molecular mass here is going to be from the periodic table. And so that should be, what's 32 plus 4? So this should be 34 grams for 1 mole. It's a 1 to 1 mole reaction based off our chemical reaction. And this is 1 mole for every 2 grams. If you didn't see those numbers where they come from, hit hard pause, ask for some help, and I'd love to help you out. If you see where those numbers came from, you're in a really good spot. This is kind of like we're just putting a cherry on top of things we've done. We're just like level 1, level 2. This is like a small level 3. Well, I might think it is. But in any case, that's it. So what we're going to do is we're going to take 12 divided by 34 times 2. So 12 divided by 34 times 2. That's not right. Something's off. Nope, that is right. No, that's right. That's right. That's right. I thought I punched in my calculator wrong. We have 0.71 grams of this is hydrogen. So out of my 12 initial grams of hydrogen peroxide, we actually only less than 1 of that is hydrogen. So what if we do the same math with oxygen? Well, the first half is going to be the same. So it's 12 grams of H2O2 over 1, 34 grams of hydrogen peroxide over 1 mole of H2O2. I probably should have done a different color. And then we're going to go from 1 mole H2O2 to 1 mole of O2. We're going to go to oxygen this time. 1 mole of oxygen. Just make sure I'm not running out of space here. Not running into the camera. And that is going to be 32 grams of O2. So we got 12 divided by 34 times 32. And that gets us a whopping answer of 11.29 with a rounded answer going there. So actually when we have our 12 grams of hydrogen peroxide, it is not an equal split. 0.71 is hydrogen and 11.29 is oxygen. If we add those two numbers up, that is 12 grams. Now, sometimes you're going to notice there might be a small discrepancy due to rounding. That's okay, not too concerned. But I want to kind of hammer in the fact that when you're looking at stoichiometry, you can't go from grams of one thing to grams of another. It just can't happen. There's some steps you need to do in the middle. I know they're long, but after a while, you're kind of just going to be pro at this, or at least hopefully going to be pro at this. Let's apply this to a true limiting reactant problem. Okay. I'll maybe hit pause in the video, and I want you to read this first, read it a couple times, and then hit play, okay? But I'm going to go ahead and get started and just roll, okay? At high temperatures, sulfur combines with iron to form iron black, iron 2 sulfide. It's just a written way. I'm pouring my coffee. All right, don't judge me. I'm making a video at 10 o'clock at night, all right? Okay. Just make sure we're on the same page here. Iron, where's my little mouse? There we go. Iron solid, sulfur liquid makes iron 2 sulfide, which is a solid. In one experiment, 7.62 grams of iron is allowed to react with 8.67 grams of sulfur. What is the limiting reagent, and what is the reagent in excess? Ooh, hard time. And then how much of the iron 2 sulfide is formed? So we don't know which one's going to be limiting reagent. We can find that out, though, by converting both of these into iron 2 sulfide. And then we're going to compare those numbers. So let's just do that, okay? We have 7.62 grams of iron, and we're going to convert that to grams of iron sulfide. Cool. Let's just do it. We got 7.62 grams of iron over 1. And, ooh, I need to pull up my periodic table because I don't know some of these numbers off the top of my head. There we go. We have 56 grams of iron for 1 mole of iron. Again, if you don't know where these numbers are coming from, you can either pause. I'd love to help you out, but I'm going to go with the assumption that you understand where these numbers are coming from. Okay. For every 1 mole of iron, we produce 1 mole of iron sulfide. And every 1 mole of iron sulfide produces, well, how many grams is that going to be? That's going to be 56 plus sulfur, which is 32. That's going to be 88 grams of iron sulfide. Cool. Let's figure it out. So 7.62 divided by 56 times 88. That's going to give me 11.97 grams of iron sulfide. Let's use a different color. So now let's go from 8.67 grams of sulfur and figure out how many grams of iron sulfide that makes. And then we're going to compare the two numbers. Let's make sure I'm not going to run on the way to my camera. Okay, we got 8.67 grams of sulfur. Let's go a little bit thinner on that line so we can make sure I can see stuff well. We got grams of sulfur to 1 mole of sulfur. I should probably have a paper periodic table here. Anyways, 32 grams. Let me know. What works better? Do you like the thicker lines in the video or the thin lines? I don't know. Which ones look better in the video? Which one's easier to see? I'm curious. All right, we got 1 mole sulfur and 1 mole of iron sulfide. Looks good. And then last step, 1 mole iron sulfide to 88 grams of iron sulfide. Okay. So we get 8.67 divided by 32 times 88. And that gets me 23.84, rounded to decimal places, grams of iron sulfide. So we've done all of the work. We're done for answering these questions. Okay. What I'm going to do now is now look at these numbers and see what is this information telling us. So if I mixed 7.62 grams of iron with 8.67 grams of sulfur, it produced something. Well, which one of these produced a smaller number? Well, that's 11.97. So what we can say then is that the iron is your limiting, and the sulfur is your excess. Since theoretically the sulfur made more than the iron did, that's how we know the iron is limiting and the sulfur is excess. By doing this method, we also predict what's the amount of mass formed. That's 11.97. So by doing these two things, we actually knocked out the whole problem in one get-go. That's it. All we're doing is doing gram to gram stoichiometry and comparing those numbers. That's all we're doing. So this problem looks ugly. What I want you to do, take a deep breath, pause the video, read it again, and then do it with me, okay? Or being awesome and just do it by yourself. Okay. Acrylonitrile, C3H3N, is the starting material for synthetic fiber acrylics. So like acrylic nails or acrylic fibers, often used in some athletic clothing. Anyways, can be made from propylene by reaction with nitric oxide, NO, as follows. So what mass of C3H3N, so I'm just going to write some things here. We're looking for how many grams can be made when 21.6 grams of propylene reacts with 21.6 grams of nitric oxide. Now, the chemical reaction is already balanced, and we actually can ignore these other things. We don't need them. We're only looking at how much can be made. So let's do the exact same thing we did earlier. So we got 21.6 grams of C3H6, and we're going to convert that to grams of C3H3N, or acrylonitrile. So grams C3H6 for 1 mole C3H6. Well, that mass is going to be 12 times 3, so 36 plus 6 should be 42. All right, for every, 4 moles of C3H6 we have in our chemical reaction, we actually produce 4 moles of C3H3N. Okay? Looks good to me so far. And then last thing is we're going to go from moles of acrylonitrile, so C3H3N, to grams. So it's going to be 36, it's 10 o'clock at night, so let's make sure we're doing our math. 36 plus 3 plus 14, 53. Sweet. All those units cancel out. Oh, that's just so fun to do. So I got 21.6 divided by 42 times 53. And we have 27.26 grams of C3H3N. Cool. All we need to do now, and let's do it in a different color, is go from 21.6 grams of nitric oxide and convert that into grams of acrylonitrile. So it's 1 mole of NO. Ooh, NO, that's going to be 14 plus 16, 20, 30. For every 6 moles of NO, we actually produce 4 moles of C3H3N. And for 1 mole of C3H3N, we use or produce 53 grams. Cool. I think we're done here. Now, here's a good thing I want to point out. A couple things. One, notice this part. Let's do a little bit bigger. I don't know if I can do it bigger. This part right here at the end is the exact same as this part right here. Okay, I want you to notice that pattern. Since we're both going to the same product, they're actually, the second halves are exactly the same. So don't redo the work. Just keep it nice, straight, and organized. Okay? Second thing I want you to notice is that everything is one continuous line. When you're doing stoichiometry problems, since we kind of learn things bit by bit or piece by piece, you might be inclined or really want to kind of do it piece by piece. I just don't recommend it. But in any case, 21.6 divided by 30 times 4 divided by 6 times 53, I get 25.44 grams of C3H3N. Okay, so theoretically, if we were to mix those two things together, what would you make? Well, whatever is the smaller one is your theoretical yield, how much you would actually make. All right, so we know that this is the limiting nitric oxide, and your acrylonitrile, not acrylonitrile, your propylene is excess. Okay? Now, I'm going to give one heat of warning. I've got no problem with online resources. But what I'm going to consider finished here is we're going to look at limiting reactants and call that done. We're not going to go one step further, which some online videos might do, whereas looking at how much is left over. I think that's a little bit beyond the scope for my class, so we're just not going to touch those problems. I want you to try kind of the next couple warm-up questions. I'm going to have an answer key for those posted in class. If you want to see them, cool, let me know. You guys are awesome, stay awesome, and I will see you in class. Take care.